Thank you all very much for inviting me, and especially Bob for guiding me through and telling me what we're doing here. So basically, we are watching people work on computers in education in many areas, domains, and we are figuring out what their emotion is, and we're predicting what their behavior is, and we're predicting the performance that they're making. In other words, we're trying to do what a very capable, talented teacher would do. And so I'm just going to take you through a few of those items. So we are asking questions like, how can a computer perform continuous assessment of a student, of their outcome and behavior? How can we create synthetic partners for the kids to work with? How can we detect emotion, create avatars, then respond after we detect what the behavior is? Is the child frustrated? Is the child in line and in flow? Is the child aggravated? How do you then respond to that? What do you do when a person makes mistakes or asks for hints? And how do you tailor messages? In other words, we're looking to do what an expert teacher does, and we're not doing it just in grade schools. We've been using these systems with community colleges and higher ed as well. So basically, we just videotape somebody, and this is an actual, in fact, all the slides I'll show you, the pictures are people who are actually working with a math tutor. How do we predict what they're going to do in the exercise? What's their outcome? I mean, we actually have to say, are they succeeding? Are they asking for a hint? Are they going to fail? And we want to provide the appropriate interventions. So if you guys have questions, that's fine to ask while we're going. So here's some other pictures and what we've been doing. Oh, I'm sorry. This is the agenda. We're going to look at continual assessment, like all the way through. If it's 30 minutes, how do we assess what the student is doing? And then the synthetic partners, and then the predicting, and then we automate instructional content. That is, we actually create questions, check answers of text, not just right and wrong, but when a student submits text, can the system actually understand it? So here's some more people. And as you can see, for those who are in computer graphics, we're tracking the eyes, we're tracking the mouth, the nose. I mean, people know about this: gaze direction, head pose, facial action units, and I'll show you some of those. And, you guys have been doing it in computer science and computer vision for a long time. We're trying to recognize what the mind is doing while we're tracking these facial features and gestures. So again, these are real people using our system, and the one in the third down looks like she's falling asleep. The kid below looks sort of interested. The one at the top looks a little confused. So we are trying to correlate. Right now, you and I pretty much don't know what any of them are doing, and teachers don't know for the most part. But we are pretty sure the computer is going to figure it out. Okay, and here's one way. These facial action units have been tracked for a long time. We're going to try to identify them, find out how they relate to teaching. And so you see again, I didn't do these action units. These have been done for a long time. The eyebrow, the razor, and then you go to the right, the lip tightener, the inner nose wrinkler, the lip correlator. So we are detecting each of these items, putting them into uh, into a long-term, a long short-term memory unit and a recombinant neural net, and asking the network to figure it out. And we're getting somewhere. So that's pictures from OpenFace. What we do is have, in this case, 51 sixth graders, male and female, 968 videos of students working. We extracted the timing information for each exercise. So they are asking for a hint, they get it right, they get it wrong. We're recording all that and then trying to correlate it with the facial expressions that I just showed you. So, and then we label each video with the success rate, the number of hints, etc. We developed an affect model. That means that affect is, of course, emotion. So that we're attributing to every one of their behaviors frustration, flow, excitement, anger. And the predicted student exercise. Sometimes we were able to predict in the first 5 seconds, and I'll show you that later. In 5 seconds, we were able to predict what that student was going to do. Were they going to solve it? Were they going to ask for a hint? Were they going to guess? Were they going to not read it and just fly by it? And this is how we do it. Again, this is a real student. And at the top, he did SOF, which for us is solve on first. And that's good. And you see he's raising his hand. He's quite happy with what he did. The middle one, he's asking for a hint, and he's a little confused. I mean, you could tell that sort of. And in the last one, it's not clear, but he did give up. So we have all these recordings on the left, and we have the video. And then on the right, we've explained what the efforts are. SOF, as I said, was solved on first. AT&T, he attempted, but then he self-corrected. SHIT, he asked for a hint. He asked for help down here. He guessed. Okay, then these are the positive, of course. And these we say are the negative. He guessed. He didn't even read it. We think he went too fast. He skipped and he gave it away. He gave up on it. All right, so all this is being tracked for 30 minutes or so. And then the system makes a prediction. And in brief, it's that there's a person who's confused or whatever. We're looking at an affect network, which is we're looking at other people who have, where this has been analyzed before, people who look disgusted or look angry or look happy. And we try to correlate that with the person that we are looking at. And in brief, it's that we look at the affect network that's, as I said, a large network of already understood or labeled folks. And then we do our units, our head pose, a gaze estimate, and then we come out with a prediction. It was all H predictions. And it's that he asks for a hint, or he's going to skip, or he's going to solve on first. And I'll show you the kind of results we're getting to do that. So in terms of emotion, this is a little bit of psychology. Literature shows that positive emotions, confidence, improve performance. Negative emotion, low self-confidence can reduce performance. Boredom reduces performance, and student interest supports learning in general. What we do is use, as I said, a deep neural network, recognize the direction of the student's head as they use the tutor. If students are not looking directly at the screen, they might be distracted. That's in addition to picking out what their emotion is, and the tutor can bring back their attention. So we've used a fully connected neural network trained to detect the presence and intensity of the 3 action units. So we've decided on AU4, smile, AU9, nose wrinkle, and frown, AU12. And we're putting those together and see if just doing that will predict what the student is going to do, et cetera. And we use a TensorFlow, and the model is trained on a data set of 35K face images labeled with 68 face landmark points. And as I said, it's eyebrows and nose, et cetera. And then, right. So this is very confusing, but we're back to the same action units here, the eyebrows, the cheek razor. But underneath it, we have correlated each of those facial features with our effort list. Our effort list, remember, had an asked for a hint, give up, guess, no, didn't read, asked for a hint, etc. So it looks like the brow, lowering the brow, has a high correlation with each of these efforts. In other words, when kids were showing these efforts, there seems to be a large correlation with the eyebrow, and similarly with the lid tightener, and similarly with the chin raiser. But some of the others, here, there seems to be no correlation with the upper lid raiser. That was the brow lowerer, right? Okay, lid tighten. So the x-axis is the outcome of what that student did. Did they give up? Did they guess? The x-axis. And the y-axis is the area under the curve, so to speak. So we're starting to see which of these AUs really work with these action units. And this is, there are other databases that we use of adults, but I just thought this one was nice to show. So some people humans, that is, have labeled angry, open, happy, disgusted, etc., fearful. And we have taken off from the children's databases, and we use several of them, and then gone to the adult database and made similar comments and linkings. And so here we are still again, we're still on the open source tool. We're looking at 68 facial landmarks, looking at the eyes and the mouth, the head orientation, the gaze direction, 18 facial action units, and 17 facial action units intensities. And we concatenate all the above and a feature vector length of 8,000, pass it on to a long short-term memory-based recurrent neural net. Okay, so that was continual assessment. You maybe now believe we can do continual assessment if we keep watching the student. I'm going to move on to synthetic partners. How do we get the student to talk to the system and pretend that it's someone trying to teach them? So we have this system that we've been working with. It's called MathSpring. Again, it's been used at higher ed. It's been used at community colleges. It's been used at grade schools. And the system will read the problem to you, give hints, replay hints, etc. And this is just one problem, fractions problem, or preparation for fraction. What's that? Okay, so I'm not going to show you too much more of it, but a lot of the responses that we give, that the system gives. Is that a question? Does someone have a question? Okay. So we like to talk not to the student about whether it's right or wrong. We like to talk to the student about what we call growth mindset. Something like, did you know that when we learn something new, our brain actually changes? It forms new connections inside that help us solve problems. Pretty amazing, huh? And studies have shown that students who believe that intelligence can be increased tend to seek out academic challenges. So if you believe that your brain can change while you're working, you might work harder, etc. And this has been proven true. And now here's the same thing. There's no single way to learn, etc. This is what our companions tell people. And this is a visual acknowledgement of has anxiety. I often get discouraged when struggling with a math problem. Although I think that more important than getting the problem right is putting in the effort and keeping in mind the fact that we can all be good at math when we try. So almost all the responses are like that. And our system talks to the student, and we've tested 3 different ways to respond. Empathy, don't you sometimes get frustrated? I do. Growth mindset, which I just talked to you. Did you know that when we practice, our brains grow and get stronger? And this is the one that I told you we don't like to use, success failure. Yes, you got it right. No, you got it wrong. And then we've done studies to show that these lead to different reactions among the students. So we did 61 students. All students completed a pretest. We had an event log, recorded 3 classes over 4 separate days. And we gave them these different messages. So we gave them the empathy, the growth mindset, and the success failure. And then we asked students later how they're or before and after. Are you interested in solving math? Are you excited by it? Are you confused? Are you frustrated? Learning orientation, performance, etc. So what we want to do is link the responses that our system gives with whether they change their ability, their liking of math, their excitement in it, their interest. And what we've shown is that there is a high correlation between their interest and empathy. So when you do the empathy one, well, I get frustrated too. They seem to have an increased interest, and they seem to have increased math value. That is, they think math is more valuable. But interestingly, if you tell them the growth mindset, which we thought would be very powerful, it's a negative change. In other words, their interest in math, their thinking about math, the value of math goes down, and their performance goes down. That is how many right or wrong they get, which we haven't quite explained yet. And then the other is that success failure. Say, yes, it's right. No, it's wrong. That it leads to more confusion, which we thought would be the case. And it leads to a learning orientation being negative, inverse proportion. So it's interesting. It's not all one, these interest and confusion, but it seems to react or respond to messages of empathy or messages of growth mindset, that the mind grows, or the yes, no kind of response, which is great. Because I mean, these are things a teacher can't do because they have 30 people in front of them. They can't really understand this, but I'm thinking that the system can. So the observation is that with exposure to more empathetic messages, students exhibited higher levels of interest and valued math knowledge more. And that was empathetic. You know, I sometimes get frustrated too. Growth mindset is when you say, well, you know that your brain actually changes when you learn something. The students seemed to get more problems correct on their first attempt, yet they valued math knowledge less and had lower post-test performance scores. And this one I told you we're still working on. And the success failure, yes, you got it right, no, you got it wrong, were the students seemed to be less learning orientated. They didn't want to do it anymore, and they seemed to be more confused. And as far as the character goes, well, I don't have to go, but again, the success, when you say yes, it's you did it right, kids get more bored and have more anxiety. And almost all the tests that are online do that. They say yes, no, and that's all they do. Okay, so that's the partners. And what I want to do now is just say how we are predicting learning. As students work online, they demonstrate these emotions. And what we want to do is predict them ahead of time, like in 5 seconds, which is what I'm going to show you that we do. So the student is solving a problem and we are recording what they're doing. And there are 8 possible behaviors. They attempted the problem, they gave up, etc. They skipped. And what we're doing is using deep learning neural nets for facial features to predict their outcome. This is an interesting point here. There are so many problems that you can choose in math, the thousands of problems in the standard, say grades 4 through grades 8. Which ones do you take? And what we want to do is take problems that make them more engaged, that keep the student involved. That is, don't give them all easy ones, don't give them hard, but kind of gradually go up on some level that it gets them more engaged. And we were able to do it by choosing problems. These are the problems. These are 6th grade and 7th grade. Let's see, ratio and something else. And this is the behavior of the students, solved done first, But we also measured, what's nice is their mastery level, actually asking them how well they did in each problem. But then a record here of the problem difficulty. And if you'll see, the problem difficulty is sort of straight away and then gets a little harder and then gets a little easier. I mean, we're just measuring the difficulty of problems, a fraction problem, there's kind of a graduation of easy ones to hard ones. So when we go a little bit harder on the problems, their mastery seems to go up a little to keep track of it. And then it seems to go down when the problem difficulty goes down. And this is amazing because if a teacher could take each student individually and give them exactly the problems they need at the time they need them, we think teaching would be much more effective. So in terms of this problem difficulty, there's a difficulty level for each problem, and we run the model for each difficulty level in order to figure out which new problem to give to that child. And we select a level that yields a positive problem outcome. We know we can predict what they're going to do, and I'll show you that. And then we're also, this is going back to what you saw before, we predict student attention as they use the tutor. So if there's somebody starting to look up, we can recognize that. And we say, hello there. And this one's looking off where she's gazing. Hello there. Shall we continue now? And this is a location of the student's head. Again, this is just computer vision. But what it is, let's see, the orange is up and down. The head is going up and down. And this blue is the left and right. And this is the, I forget. The second chart shows head tilt, just the tilt. And what we found is that we can predict, we can see, we know from the log data what they got right, what they got wrong. And here's a child that did a lot of this kind of activity and then solved the problem on the first attempt. And we've got others where they solved the problem on the second or third attempt, and then they gave up, and we can see what the behavior is. So the fully connected neural network was trained on a data set of 35K face images labeled with 68 face landmark. And again, it's just what I showed you: eyebrows, nose, mouth. Output contains confidence prediction, etc. And this again was 68 undergraduates using MathSpring, and faces were videotaped, resulting in 2,000 recorded problem-solving interactions. To assess the model accuracy, we ran head pose estimations with 340 images, and 2 human coders were asked to label the images. And then we kind of asked the humans, what do you think the student will do in terms of, and we of course know what the student is going to do because they're seeing the video later on, and we already know how they succeeded or didn't succeed in that problem. And we found a strong connection, accuracy when comparing the human annotations with what our system is getting. So I guess I didn't show you the numbers, but facial and gesture recognition is combined with not only log data, which is just following exactly what they did, but self-reports. We also asked them, do you think you'll get this right? Was this difficult, etc. And the combination of the head position and the facial expressions and the logged problem-solving activity provides invaluable data to detect what the performance is. So the last item is the automatic development of instructional content. So once we're getting to a point where we can predict what they're going to do, and we have synthetic partners that can talk to them, and we're continually assessing the kids, then we're going to say, can we actually create the problems and create the questions? And we're not talking about yes, no, or multiple choice. We're talking about real textual problems. And once we can give the kids textual problems or ask them for textual answers, do we know what to do with that? Can the system actually evaluate their statements, with their text? And then finally, we should just give the graduate degree to the computer because the computer's doing all the work, right? Anyway, this is the latest part, which is the prompt for ChatGPT. And we're saying to the computer, you are a math teacher with 10 years of experience teaching math to K-12 learners from diverse backgrounds, including a variety of socioeconomic, cultural, and languages in the United States. I will give you a math word problem. And as I told you, we have 1,000 math word problems. And I will give you a multiple choice question or short answer type, along with the hints needed to solve the problem. I need you to generate the same number of hints as given in the problem. So if I show the system a problem and I ask for, I could ask for multiple choice questions, but we also want short answer, which is when we ask the student to explain what they did. And then we say to the ChatGPT, how would you improve each hint from the perspective of the math teacher? I will also give you what grade each problem is from. So we use variations of this, and a lot of different people at UMass is doing this, several different groups. My first math word problem is such and such, and I'll give you an example, but you know what math problems look like, you guys, you all do. In this first area, we're going to look at how to generate these hints. So we're going to give MathGPT a problem, and then we're going to ask it to generate the hints and show them the kind of hints we have. This can significantly benefit students grappling with math word problems, and the teachers must be involved in reviewing the hints, whether human crafted or transformer generated. So this is a problem in math. Find the value of x in a right angle with a line at 62 degrees, where x is the complementary angle. That's pretty straightforward. So this is the first hint that we showed to ChatGPT, the second, the third. And sorry, I'm on the next step over. This paper was actually said to ask a teacher to evaluate the following hints. This is a hint that was produced by the human, and this is the one we sent to ChatGPT, and we asked it to improve on that hint, and this is what ChatGPT produced. And again, the human produced that hint, and ChatGPT produced that. And what ChatGPT did was just simply kind of add to this. The human said complementary angles, two adjacent complementary angles form a right angle. And then ChatGPT says when they are adjacent to each other, they form a right angle. Think of a corner or an L shape. So it actually added some material. And then we brought all this stuff to, we call them pre-service teachers, folks who are studying to be teachers. And we say, which hint did you like better? And in half the cases, we gave them 5 different problems. Half the cases they wanted the ChatGPT hint, but we did not tell them who had produced which hints. So we looked at 33 pre-service teachers. We asked them a survey to collect their perception and responses for 5 problems, math problems. Human crafted, which is here. Transformer generated, which is here. And then why did you choose this variant? To eliminate bias, we didn't tell them, and the paper is here. So these slides are all going to be put up by Robert Krovitz, and if you want to see, read any of these papers, they're available. So the pre-service teachers prefer transformer hints when the hint provided details about the problem. In other words, when ChatGPT kind of expanded and said more about how to achieve this, the teachers who looked at the results really liked it more. Number of responses of people who who chose the transformer generated hints. And this was the question, and I have, you saw some of the answers. And so this is one question, a math problem. Find the value of x in a right angle. That's where we just looked at. Which of the following symbols make the following inequality true? And again, the humans preferred the transformer generated hits. So these are teachers preparing to be, these are pre-service, these are folks preparing to be teachers. And let me just tell you that we looked at the words that the teachers used just to identify the themes of what they said. So even though this looks very complicated, it turns out that this was the respondents, this is what the pre-service teachers said. And they do seem to fall into 4 clumps. And we then organized the clumps and figured out what words people were using. And when the transformer hints were analyzed by humans, the human teacher said the language is more descriptive, the explanation of the right angle. I feel like when it comes to applying concepts, it's, I don't know, even if the previous 2 hints led up to the equation itself, having this hint appear like this might draw the hints to da 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 da, and this coincides. Anyway, seems like the transformer was giving more explanation, was giving more guidance, and also gave simple walkthroughs. So it leads the student to the correct step. And the human hints were liked for half the time, but kind of was too narrow for the teachers. They wanted it a lot deeper and longer. So then there's the idea of using ChatGPT to produce these problems. So what we can do is load large text. You can load a chapter in about DNA and upload a document, a PDF, and then receive. It can say to ChatGPT, give me a single paragraph with bulleted items, or ask for a summary, or produce the test question. And in every case, the ChatGPT can actually produce the questions that we're asking the kids. So here's an automatic text grading. So let's say the human created this passage. Long ago, a poor country boy left home to seek his fortune. Day and night he traveled, stopping to eat at inns, etc. Describe the kind of person this merchant is, and give one detail from the story. And so we asked students responses, and this was graded by the LLM. In other words, the system knew what we had put in, what we had asked teachers, and then just looked at the data set to see whether this is what a student produced. And the LLM just looked at that and tried to give it a score. And in this case, it scored very highly for the merchant is optimistic and perseverant, and it states that he kept walking. And this answer was kind of short, that the student only said something short. He gets a 2. And this student said dishonest because he didn't want to pay for the eggs. And that was not only brief, it wasn't accurate. But you guys don't know the whole story, so it doesn't look like that. But anyway, we have experimental results where we look at QWK, which is a metric to compare the consistency and fairness of grades given by different teachers. We looked at how the humans were grading the students, that is, what numbers they were giving for the answers that the students gave. And we looked at BERT, and we looked at a meta-trained BERT in context. In other words, we gave BERT the questions that I just showed you. And the kappa is pretty high, and the p-value is pretty small, which is good. The smaller, the better. So the system is starting to understand short answer questions as well. And this is more, this slide should have been earlier. The system, the LLM is able to predict that this is an answer from students, all student answers. And this one has poor spelling and poor grammar. So merchant are a good man because he played the innkeeper and kept his, and the LLM says that that's going to get a 2. It's going to get a 2, but the human grader said it's going to get a 3, which is a little weird, but it gets better. And human error and subjectivity, no reasoning. The merchant is dishonest because he doesn't want to pay for eggs. It's that one got from teachers a 1 and from the system a 3. The merchant is greedy because he gives the innkeeper eggs, but when the boy asks it. So this is not yet perfected, but this is the kind of thing that is being done by Andrew Land, who's another professor in my department. And this is another example of grading student explanations. Here's the prompt. First you say to the LLM, starting with mRNA, leaving the nucleus, list and describe 4 major steps involved in protein synthesis. So you all know that ChatGPT can certainly answer that. And this is what it answered, that these are the key elements of an mRNA leaving and going to the nucleus. It says RNA exits the nucleus via the nucleopore, RNA travels the cytoplasm to the ribosome, etc. And this rubric, I'm not sure that who gave us the system that said that these if you get 4 key elements, you get 3 points. If you get 3 key elements, you get 2 points. But anyway, once the student's answer comes in, the system can then analyze that and it looks at each line and says after RNA, the student said leaves the nucleus, and that's exactly the same as that. So the child gets a score for that A. It's a college student, and it travels to the cytoplasm, to the ribosome. It goes to the ribosome, so that gives you another point, etc. And so the machine is actually grading this. And then the limitations for LLMs are the same as they are for every field. There's hallucinations and incorrect statements. The data is subject to algorithmic bias in terms of gender and race and culture. And the effectiveness of this whole system can vary based on factors like the student preparation and prior knowledge, the subject matter complexity, implementation quality, etc. And then it's also dependent on the neural network being used. And you must train that to, and first of all, set it up so you can ensure diverse, ethical, and inclusive instruction. And the models can exacerbate falsehoods that are in the model to begin with, inaccuracies. And the texts produced by LLMs are difficult to explain. So there's nothing new in the limitations of LLMs, but it gets more serious when you use it in education. So this is my last section, I think, pretty close to last. And what I'm doing is going back with you've seen this already, open face, so we're still looking at the facial features and concatenate all the above and put it into a long short-term memory-based RNN. And this is to predict their engagement. And this is when we used a mobile net, so pre-trained image net, which I didn't show you, but it's like the children's database, has lots of human pictures in there. We use that to train the system and to predict student engagement using different deep learning and head pose estimate approaches. So it's a classification task, essentially. And what we found was that the best results were obtained by the model with less complexity. In other words, it accurately predicted what the student will do. Will they ask for a hint? Will they fail? Will they guess? Will they quit? Etc. And what I like, I mean, now you see that we're up to 94% accuracy. But what I like is to recognize that it's all happening within 5 seconds. Between 5 seconds and 20 seconds, we are predicting whether the student will give up. Oh, sorry. Whether the student will give up, will guess, will not respond, will not read it is what it is, ask for a hint, etc. So this is the student if effort. And this is the video length that we're looking at. And we're looking at video from 5 seconds to 20 seconds. So for something like skip, somehow the system can tell right away in 5 seconds that this person is going to skip. You know, maybe they're just going, not even reading it, going so fast that they're not reading it. And similarly, for not reading, we can tell right away from their facial expression and their hands that they're not reading it. Whereas these other guys, if they're going to ask for a hint, sometimes it takes longer because they have to think a little bit about it and they're not getting there yet. And this is the same thing. And what we did is look at 2 behavior outcomes, whether it's going to be positive things like he's going to ask for a hint or he's going to get it on the first or he's going to respond. And this is the actual F scores for 20 seconds, 15 seconds, and 5 seconds. So the longer you wait, the better our results. But in fact, and EPAT is just the name of our system, which does this visual and timing information. But the longer you wait, the more log information you have. So the visual information comes immediately, but the log information takes more time. And that's why you get better results down here. But these are pretty good F scores, in other words, very close to actual prediction. So we are pretty much done. And some of the conclusions are early outcome prediction provided by combining timing information with visual affect analysis. The visual information is available as early as 5 seconds. We have superior performance of facial recognition over baselines and previous state of the art. And that was a publication of AAAI, actually. Affect messages build student-tutor rapport and influence students. Empathetic messages seem to result in improved student interaction experience, and empathetic messages also result in students saying they have more confidence, saying they have more patience, higher level of interest, etc. And these success failure messages that I showed you that just say you got it right or you got it wrong result in more mistakes and less learning orientation, etc. And then the contributions here are proposed new student engagement video data set, use advanced conversational AI techniques, the LLMs, to personalize the instruction, use deep learning approach that outperforms traditional head pose classifiers, explore the influence of emerging large language models, compared LLM generated content to human created hints, and interventions from virtual companions are presented when student wandering is detected. Okay, so we're getting there. We certainly don't have it done by any sense of the imagination, but it looks like the computer can know more about understanding the student than do most teachers. Thank you, and if I will entertain any questions you all have.